Hey guys, so today in this video I want to talk about the peculiar properties of d orbitals, specifically the 3D orbital. And this is going to be like a series thing where in this video I'm going to talk about the filling of 3D orbitals with electrons. But in my next video I'll talk about the splitting of the 3D orbitals that occurs because of that occurs in the crystal field theory, and also the involvement of the spectrochemical series. So for now, let's just take a look at what we're gonna explore today. And so, yeah, the first thing we're gonna explore is the fact that the 4s subshell gets filled before the 3D subshell, right? Even though the 3D subshell is an inner subshell, its principal quantum number is 3, which is lower than that of the 4s subshell. And so this is explained quite well using a phenomenon called penetration. And I'm going to go over that in a sec, but if you look at the other thing that we're going to explore today, it's actually quite contradictory to the first one. It's about what happens when we form ions of transitional elements, right? Specifically cations. So during ion formation, what happens is that instead of losing 3D electrons, we lose 4s electrons, right? Even though here we stated that 3D orbitals have higher energy. Like 3D orbitals um, are filled much are filled after 4s orbitals, right? And so if they are kind of like the valence electrons, then shouldn't electrons should be removed from the 3D orbital before they are removed from the 4s orbital? And so that doesn't happen, right? So I'm going to explore that. But first, let's take a look at penetration. So what happens in penetration is that it's the ability of an orbital to bypass the shielding of inner orbital electrons, right? And so basically, this idea of penetration is based on the radial probability distribution of orbitals. And like, I'm just going to take an example here. So if you look at the 2s subshell and the 2p subshell, what happens is that the 2s subshell shows penetrating effects, right? So in this graph, you can clearly see uh, that the 2s subshell is farther away from the radius, right? This peak you can see from the radial probability, this radial probability graph. This peak in the probability is much further away from the nucleus compared to the 2p, the peak right here. And so why does the 2s orbital still have lower energy even though it's further away from the nucleus? And so that is explained by the fact that there's a peak here, a small peak in radial probability here that is much more closer to the nucleus. Now, the peak occurs before this node, and so this peak is actually called a subnodal maxima. And what happens is that because there's a peak here, the overall energy of the 2s orbital is lowered. As a result, we see that the 2s orbitals are filled before the 2p orbitals. Remember, when energy is lowered, we're going by the, what was it, the off-ball principle, right? So we start from the bottom, build up based on the energy, right? So the lower the energy, we fill up those orbitals with lower energy first, and then we move up. And so because we have this peak here, it's kind of showing that it's penetrating the 2p orbital, right? So at this place, the penetration takes place. And because of the penetration, the energy is lower. And so this is also seen with 4s and 3d orbitals, right? As we can see here, the 4s orbital is much further, the peak, this peak here is much further away from the nucleus. And the peak for the 3D orbital is much closer. However, we're only taking these peaks into consideration. When we take the other peaks, we see that there's also this small peak here, the small subnodal maxima here, that basically serves that basically is an example of it's an example of penetration, right? We see that the 4s orbital is penetrating the shielding of the 3d orbital, which is why there's still a chance there will be a chance that you will see the electron density much more closer to the nucleus. And so this was penetration. Now, if we take a look at ion formation, we like after we move on from penetration, it's gonna be weird, right? Because look, if we take zinc as an example, we would predict that, of course, zinc has its own ions. It's zinc 2 plus. And so what we would assume that the two electrons it would lose to form that ion would come from 3d orbital, right? Because again, from what we established from penetration, 3d orbitals have higher energy compared to the 4s orbitals. So that would mean that the 3d orbitals would lose two electrons, right? Now, that would be the case if the assumption was true that 3D orbitals are actually higher in energy when all the orbitals are filled with electrons. But that is not the case. If we look at the actual electron configuration of zinc 2 plus, we see that it loses electrons from the 4s orbital right here. And why does it lose electrons from the 4s orbital? This could only mean one thing, that in this situation specifically, the 4s orbitals have higher energy compared to 3d orbital. But why does that happen? We just established from penetration that 3d orbitals have higher energy. How come now all of a sudden 4s orbitals have higher energy? So this is really weird. But there is explanation for this, and it will provide you with more intuition. So what I want to do right now is, so I want to show you guys this cool graph here that describes the energies of the 3D and 4s orbitals clearly. And so if you take a look at this graph right here, it represents the energies of the 3D and 4s orbitals with respect to the atomic number. So just from the variables of this graph, you can assume that definitely the energy of the orbitals is heavily dependent on the atomic number, since we see changes happening here. Now, the interesting thing here is that, of course, according to penetration, we would expect the 3D orbitals to have higher energy. Now, that is not always the case. It is the case until until the element 21, the element with atomic number 21. But after that, the 3D orbitals have lower energy, right? And so this kind of resembles like this. The reasoning for this, we can explore this more through a periodic table. Basically, what happens is that this this crossing over of energies, right? The sinking of energy of the 3D orbitals, it begins at around period 4. So period 4, we have potassium and calcium right here. And so that, again, this, all of these, let's look at the blocks. This is the S block, this is the D block, this is the P block, this is the F block. So right now at the start, we're looking at the S block, and that is for s orbitals in period 4, which means that for potassium and calcium, the 4s orbitals are filled first. And then when we move on to the D block, which represent the d orbitals, we slowly fill them up. And as we fill them up, the energy of the 3D orbitals somehow decreases. That's what it's trying to say, that as we fill these elements up with electrons, these neutral atoms with electrons, the energy of the 3D orbital decreases. And the 4s is, again, it remains on top of the 3D orbital after crossing this point. So why does this happen? This is mainly explained by the fact that on the left side you see that we have empty orbitals, and on the right side we have filled orbitals, right? So empty orbitals have different energies compared to filled orbitals. Now, specifically for 3D and 4s orbitals, what happens is that if we, let's say, consider an atom that has an atomic number of less than 19, right? Like basically its 4s 3D or 4s and 3D orbitals are empty. They have not been filled yet because it doesn't have that many electrons in the neutral atom. And so because the orbitals are empty, right? What happens is that the penetration takes priority, right? The 4s orbital penetrates the shielding of the 3D orbital, since there isn't electron-electron repulsions taking place here. Penetration can easily happen here. However, on the right side, what we're looking at is the electron configuration of filled orbitals, filled 3D and 4s orbital, and you can see that suddenly the 3D orbitals, the energy of that is decreased, and the energy of the 4s orbitals have increased. And so why is that? Like we know that in empty orbitals, penetration takes priority, but when the orbitals are filled, what happens is that the increased nuclear charge takes priority. Now, again, we're assuming that this electron configuration is for a neutral atom. Since it's a neutral atom, it will have same number of protons and electrons, which means that since the diagram on the right is of an atom with higher proton, higher nuclear charge compared to the diagram on the left, what it does is that higher nuclear charge attracts the 3D orbital closer to the nucleus, right? And it, as a result, decreases the energy of the 3D orbitals. Now, why does it attract the 3D orbitals and not the 4s orbital? Well, remember that 3D orbitals, it's basically an inner subshell, right? Its principal quantum number is 3, which is lower than that of the 4s orbital. So almost basically naturally, the 3D orbitals are attracted. And the reason why, now this thing, this what we're seeing right here is further supported by the fact that there are also electron-electron repulsions, right? And so the 4s electrons, the 4s orbitals, are pushed, they're pushed away. They have higher energy because they are being repelled by these electrons from the 3D orbitals. So since the 3D orbitals are much closer to the nucleus, what happens is that they're better shielding, and therefore they push away the 4s electrons. And so since this happens when the orbitals are filled with electrons, we see that during ion formation, for example, if we look at the zinc ion, right? We know that the electron configuration of neutral atom of zinc is it's basically this with the argon. After the configuration of the argon, we have these additional orbitals. And so when we form the ion, we take away the 2 electrons from the 4s orbital, right? And after we do that, we get the zinc 2 plus atom. And so basically the overview of this whole lesson is to, like, the purpose of this lesson is to show that although penetration is strong, we also have to consider other effects for multi-electron systems, right? for example, electron-electron repulsions, and mainly the increased nuclear charge, right? And from the previous graph that I showed you guys that showed the crossing over of energies as basically when the energy of the 3D orbital becomes less than that of the 4s orbital. From that, right, this basically provides explanation for that graph. And so it's really cool how we can have two contradictory things happening at the same time. So yeah, it's that.